Now, I'm delighted to introduce our speaker, Jesse Thaler. Jesse Thaler is a theoretical particle physicist who fuses techniques from quantum field theory and machine learning to address outstanding questions in fundamental physics. He joined the MIT Physics Department in 2010 and is currently a professor in the MIT Center for Theoretical Physics. The Theoretical Physics Lineweber Institute. In 2020, he became the inaugural director of the NSF Institute for Artificial Intelligence and Fundamental Interactions, known as IFI. Thaler is currently on sabbatical in Paris, contemplating the future of AI in physics from the city's research institutes and neighborhood cafes. And I wish I was there with him today. Please join me in giving a warm welcome to Jesse. Jesse, over to you.
Great. Thanks very much, Alexander. Great to be with you all here at First Principles. So indeed, I'm right now speaking from the suburbs of Paris in Saclay, and excited to tell you about some of the research that we've been doing on applying techniques from machine learning to understand a problem in theoretical physics known as the Modular Bootstrap problem. So I'll walk you through that through this talk today. First, let me take this opportunity to advertise the NSF Institute that I direct. The NSF Institute for Artificial Intelligence and Fundamental Interactions. And I'm really proud to tell you that we've actually been renewed for another 5 years by the NSF. And in the Boston area, MIT, Harvard, Northeastern, and Tufts universities, now joined by Boston University, excited about advancing the future of AI plus physics research. And one of the things just to emphasize, and you'll meet some of these people in the talk today, is that through IFI, we're really trying to empower the next generation of AI plus physics talent. It's really junior folks who are leading the way. Some names that will show up in my talk, Siddharth Mishra Sharma, who is an IFI fellow, who's now on the faculty at U. Also Thomas Harvey and Sam Bright-Tony. These junior investigators are really leading the way in applying machine learning and AI techniques to outstanding physics problems. And coming up in August, we had an IFI summer school that you are invited to because we were oversubscribed by something like a factor of 5, but stay tuned for the 2027 edition if you weren't able to be admitted this year. And we may also take this opportunity to announce the latest round of IFI fellows who will be joining us in the Boston area, people working at the intersection of AI and physics. And if you're an early career scientist who's looking for a postdoctoral position, be on the lookout for the competition for the next 3-year cycle. So, as Alexander mentioned, I'm on sabbatical in Paris, and one of the questions that I've been wrestling with a lot is, what does it mean to do robust discovery science with AI? And there's different definitions of what you might mean by discovery science. One definition might be that you're trying to do some theoretical calculation, and you want to have some guarantee that the calculation that you do is exact. And my colleagues at IFI who work on lattice field theory have come up with some really interesting techniques that use AI, but nevertheless have exactness guarantees behind it. Another type of discovery science might be where you have some kind of explicit verification process, a symbolic engine, or automatic theorem proving. And here in IHES, where I'm on sabbatical, we've been having a lot of conversations about what it means to formalize mathematics. My student, Sean Benavides, or I should say my former student, Sean Benavides, since he defended his PhD back in April, he and I have been thinking about statistical verification. Can you make sure that what you're doing actually has calibrated confidence intervals so that if you say 5 sigma discovery, you really know what 5 sigma means? So these are various different ways about thinking about discovery science. And today, I'm going to give you a case study that's showing how my thinking is evolving in this area, searching for new theoretical physics through optimization strategies. And again, there's going to be this question of how do I know that I've discovered something? And I'll walk you through how my thinking has evolved. So let me just start with the punchline of what I'm going to show you today. And I'll have to walk you through all these various terms here. So this is research that I did with Nathan Benjamin, Liam Fitzpatrick, and Wei Li on the conformal field theory side, as well as Sam Bright-Tony, Thomas Harvey, Andre Lucas on the more optimization side. And there's going to be a coda in this story with postdoc at MIT, Kevin Leinhoff. And together, what we've found is by combining direct AI/ML and indirect AI/ML, we find an apparent obstruction constructing two-dimensional conformal field theories with small central charges and large spectral gaps. So I'll have to explain what all these things are. So this is a type of discovery science that we're actually discovering that something is not possible, that within the realm of theoretical physics, it is not possible, apparently, to have two-dimensional conformal field theories with these properties. That's what I'm going to try to explain here today. I actually come from the particle physics community. I post mostly to the phenomenology archive when I do post. This is a problem very much in the high-energy theory world. But this is for the sabbatical project, a chance for me to explore some new research direction. And AI has helped me actually do this using AI in some sense as a tutor to help me learn about this area. But also with help from my collaborators who are definitely experts in this area, and they've taught me a lot about this field. So what I'm going to do in this talk is first just start off by talking about machine learning through the lens of physics. So AI is transforming physics research, as we all know. But many foundational aspects of AI can be translated into the language of physics. And I'll try to show you how that physics language helps me at least think about setting up problems like the one I'll show today. Then we're going to revisit this problem of the modular bootstrap, and I'll explain what that all is. But the general theme is that to confront thorny challenges in theoretical physics, we can reframe those challenges as well-defined optimization problems. And that's the reason why machine learning can be really helpful in those contexts. And then at the end, thinking about what have we actually learned here, what do I actually know, trying to explain my degree of confidence in the conclusions that we've drawn. And more generally, the lesson is that as we capitalize on emerging AI technologies, we still need to insist on robustness and reproducibility. And that's what I'm going to try to show you, my attempt to, in some sense, prove that what I'm claiming here is actually true. Okay, so let me start off by talking about machine learning through the lens of physics. So as you might imagine, as a director of an AI institute, I get a lot of questions about AI ML, and on sabbatical, I've been having to confront the hype versus reality of things in this area. So on the one hand, people talk about AI being this transformational technology that's going to change all of society. And then you have other people who will point out that machine learning is just numerical optimization, nothing special. And the reality is that both are true, and both are changing the scientific enterprise. And for me, it's actually hard to draw a distinction about what's really AI and what's really ML. For me, I find it much more useful to think about direct versus indirect approaches. So what I mean by direct AI ML, these are cases where you as the scientist control every aspect of the optimization. You define the loss function, you define the algorithm, you have control about what's going to happen. And in my field of particle physics, this has enabled incredible investigations of very high dimensional spaces through a technique called simulation-based inference, where you compare a simulation of particle physics to data collected at experiments like the Large Hadron Collider. But in this process, you really control all aspects of the optimization. By contrast, indirect AI/ML techniques are ones that capitalize on emergent behaviors in computational systems. When we train a foundation model, we often are trying to get emergent properties of that system to come through in the latent space. Or agentic AI systems, we are building a harness around foundation models or something like that, and then capitalizing on these emergent behaviors where we don't directly train for what we want. We rather capitalize on what the model somehow learns to do, even though we aren't directly training it to do it. And both direct and indirect techniques will play a role in my story today. But whether you're doing direct AI/ML or indirect AI/ML, at the end of the day, it really is true that it's just optimization in response to data. That's what we're going to do, whether we are directly coding that up or just benefiting from the vast corpus of text on the internet when training a large language model. But at the end of the day, this optimization is something that actually is quite familiar to a physicist. And we can translate the things that appear in the ML jargon and translate them into physics jargon. So for example, when you have a machine learning problem that you have some training data set, to a physicist, all I'm doing is Monte Carlo integration. So it's a little bit funny to think about training on celebrity images and thinking about that as doing an integral over the space of beautiful people. But that's essentially what you're doing, with corrections that scale like 1/√n, coming from the fact that a Monte Carlo integral is only an estimate of an integral and not the real thing. We do Monte Carlo integration all the time in physics. That's what we're doing when we have training data. When we introduce a loss function, well, L for loss function is the same as L for Lagrangian. And as we teach our students in classical mechanics, variations of the Lagrangian, looking for the stationary points of an action, that gives you the Euler-Lagrange equations. And finding the stationary points of an action, or finding the minimum of a loss function, these are mathematically very similar operations. And so you can build your Lagrangian or build your loss function and understand its behavior by looking at its extrema. When we're doing machine learning, we need some type of learnable function to learn something. And we often think about neural networks, which are highly parameterized functions with many, many parameters to update. But you could also replace it with some physics function, some function where the parameters actually have physical meaning. For example, in the research that I do, I often have functions that have symmetries baked in, and the parameters that I'm learning relate to symmetries in some way. And so, this talk is actually going to be one that has no neural networks in it whatsoever. We're going to have a physics-motivated functions that we're optimizing, and yet we're going to still use the same machine learning toolkit, even though neural networks are not playing a role. And then finally, for the optimizer, doing standard gradient descent, to a physicist, we would just call this Newtonian dynamics of an overdamped oscillator. In the case where the inertia term is less relevant, the equations of motion for a overdamped oscillator do exactly the same thing that standard gradient descent does, where the degree of damping is related to the learning rate. And there's other aspects of modern machine learning that matter, and we can talk about that during Q&A, stochastic optimization, understanding the overparameterized regime, generalization versus memorization. But most machine learning problems can be framed in this language, where I take these 4 ingredients: training data, loss function, learnable function, and an optimizer. If I have those 4 ingredients, then I can take advantage of the machine learning toolkit. And I can do this in an indirect or a direct way. Now, on sabbatical, in terms of the direct research, constraining two-dimensional conformal field theories, that's the talk today. I'll explain this plot later on. But I've also been using these techniques to synthesize multiple theoretical predictions, basically taking a giant pile of calculations in quantum chromodynamics and synthesizing them together into a coherent whole. But again, I control the loss function. I get to decide how that optimization is done. I've been thinking about robust inference, even when your simulation isn't working. But again, it's the same thing. I might have a bunch of imperfect simulations, but I can combine them together in a way where I control the loss function and get something that I can understand its statistical properties. So these are applications for my sabbatical of using AI/ML in a direct way. But then there's this whole new world of indirect applications of AI/ML. For example, using AI as a research assistant. And so you have some large language model that can give you advice about how to do, in this case, how to run this particularly challenging piece of software in particle physics. You can use it as a coding agent. There's a project that I have of generating an advice document for my PhD students, which I've been able to do with Claude Code. And then a kind of outrageous talk that I gave back in March about AI and academic publishing. It was a slide deck that was created by an AI after 2 minutes of prompting by a human to talk about a world with the line between these two is increasingly hard to draw. So a 30 minutes of a presentation from 2 minutes of prompting, kind of an outrageous thing. And the only thing more outrageous was a talk that I gave in Paris at the Large Hadron Collider Physics Conference back in May, where what I did is I took all 569 papers written about machine learning for particle physics and used an agentic AI system to create a slide deck that summarized the state of the field. And it chose from all the papers on the archive which images it wanted to use to annotate and decorate its own opinion about how machine learning has been operating in our field. So kind of controversial because they're in some sense offloading some of your thinking to the machine, but it is an example of demonstrating what you can do with AI at scale. And when at the very end of this talk, I'll give you an example of that related to this research problem. But putting this all together, we're seeing the rise of AI plus physics research that's combining physics principles, physics thinking with these AI technologies. And now we want to deploy them for the goal of discovery. And in this case, it's going to be discovery in the context of two-dimensional systems. So now I want to try to explain how we're going to translate a particular type of theoretical problem into an optimization one. And this is appearing in the context of two-dimensional conformal field theories, which is a highly constrained mathematical framework that we know a lot about as a community, but it's not my area of expertise. So we're going to take a theory. It's going to be a Euclidean theory. It's going to live on a donut. So we have our 2 dimensions of the 2 ways you can go around that donut. And we're going to try to learn some things about these 2D CFTs. Conformal field theories are field theories that have a scaling symmetry to them. So there's no connection really to the real world directly. Of course, we live in 4 dimensions, not 2, but also conformal theories don't have any notion of scale in them. A scale invariance is going to be something that we're going to have to encode into our loss function. So this is a reenactment of my sabbatical at some level. So posing a research question to Claude, the anthropic tool, and Siddharth Mishra Sharma, who's splitting his time between Boston University and Anthropic. He gave me a bucket of cloud credits to do this research, so thanks to him. And here's a research question. Please identify a 2-dimensional conformal field theory with central charge in the range of 1 to 1.15. Okay, that's a research question. So what does central charge mean? That's a fancy way of saying the number of degrees of freedom you have in your theory. So 1 means 1 free boson. And so a fractional value means that you have some type of interacting theory, but it has a small number of degrees of freedom. It's as if you had kind of only 1 particle that you're working with. You can ask the question and you get an answer. The Z5 parafermion CFT has central charge of 8/7, and that's 1.14. It sneaks into that range. And this has been known since the 1980s. So only 4 decades too late to this particular research problem. And this is showing how agentic AI systems can be really good for navigating the literature. But we want to do something new. So let me narrow this range. So let me revise my question. And please identify a 2D CFT with central charge between 1 and 1.14, narrowly excluding the window of the Z5 parafermion theory. And Claude will tell me that there's no known theories in that range. And this is a plot here that's showing what's known about conformal field theories in this range. The central charge, this is the number of degrees of freedom that's on the x-axis. And then if you want to think about this as a quantum system, the first excited state, its energy level, that's known as this delta gap. This is a theory without dimensions, so this is just a pure number. And it's known for the free boson that any value of the spectral gap is allowed. Those are these purple dots along this axis. So these are known theories in purple. And then we have these 3 isolated known theories in orange. And this bottom one is the one that Claude identified in the previous slide. And this upper bound here in dashed yellow, this is a bound set by Kellerman, Collier, Lin, and Yin, combination of papers from 2011 and 2018, showing that no theories can be above this bound. So all the valid theories have to be in this box. And then for Wei Li, his PhD thesis includes this yellow band here, a heroic calculation that he did to show that in this yellow region, there cannot be a theory. So spending a lot of time proving this narrow little slice is not feasible. Okay, this is all that's known about these, according to my collaborators. And now we can ask, are there any other 2D CFTs in this range? Could I convince the experts if I found one? Could I convince myself? That's the research question. Okay, so this is all that's known. This white space is open. There could be lots of theories here. There could be 0 theories here. That's the research question that we're trying to address. And again, a purely theoretical research question where if you can get any traction on this problem, it'll be kind of quite impressive since there's, again, very little known, and even the experts are able to only exclude very, very small slivers of this phase space. So we can now ask whether we want to use direct or indirect AI techniques to try to discover conformal field theories. So you could try to just use indirect techniques and just ask Claude to think about it a little bit more and come up with a new theory. It refuses to hallucinate, so that's a good thing. You could try to turn this into a direct AI ML optimization problem, and there have been various papers in the literature that have applied AI ML type strategies to try to approach this problem. But it's actually a pretty small literature. And it's a small literature for a reason. This is a hard problem. And there's a very well-developed technique called the dual bootstrap that has been used to exclude theories with a lot of success. And actually, machine learning strategies have also appeared in that context. If you're trying to discover something, the so-called primal approach, it's extremely difficult. And now I understand why. And we've made progress on it, but you'll see we had to work pretty hard to do it. So trying to find the full structure of a conformal field theory, that's a little bit too hard. So we're going to back up and do a simpler version of the problem, which is called the modular bootstrap. And the modular bootstrap is a necessary but not sufficient condition for a unitary 2-dimensional conformal field theory to exist. So if I'm going to find a theory, it better at least satisfy this property. And well, you're going to use machine learning to try to solve the modular bootstrap equations. So more generally, this is an example of a bootstrap philosophy that's been appearing a lot in theoretical physics by defining theoretical objects by consistency conditions. And because we're going to have equations that can be satisfied, this really seems perfect for a machine learning application. And there's indeed a number of people applying machine learning AI techniques to various bootstrap problems: S-matrix bootstrap, amplitude bootstrap, conformal bootstrap. In this case, it's the modular bootstrap. And what I'm going to try to do is satisfy modular invariance, a condition that these theories have to satisfy, and find solutions to this using machine learning optimization. So first, I have to tell you about the data that defines a two-dimensional conformal field theory. So that's shown here for an example CFT using that same orange dot color corresponding to a known CFT. So this is a particular CFT that's known. It's called the n=1 minimal model with m=5. And what you're seeing on the x-axis are the energy levels, if you'd like, of that system, which each dot corresponds to a particular energy level of the system. And then vertically, we have the spin of the system. This is a bosonic theory, so the spins are just integers, 0, 1, 2, 3. And this is a known theory where the orange dots correspond to the data of the CFT. And this is a valid theory. In fact, the dots go off to infinity, but I've cut them off because on a computer, you need to have a finite number of numbers, and this cutoff will play a role in the story. Basically, when I cut things off, I can only ask for an accuracy as determined by that cutoff scale. The data of my CFT, I need the operator dimensions. Those are the energy levels. I need their spin. I need their degeneracy. How many states are at a given dimension and spin? Spin is an integer. Degeneracy is an integer. And from this, I can compute the partition function. So this is the equivalent thing that you would compute in statistical mechanics, the e to the minus beta e, only generalized on this torus so that this tau is kind of like an imaginary temperature. And this partition function depends on that imaginary temperature. It depends on the central charge, the number of degrees of freedom, depends on these orange dots, the dimension, spins, and degeneracies of these operators. And then the scaling symmetry is basically a temperature goes to 1/temperature symmetry, roughly speaking. And modular invariance, if you satisfy this property, that means that you at least have a chance of being a CFT. You have a chance of having that scaling symmetry. That is, the system at 1 temperature versus an inverse have the same properties. And again, this seems like a perfect opportunity for machine learning. Just get the machine to solve that equation. Seems perfect. Now, I want to emphasize that we're doing machine learning without neural networks. Okay? Nothing stops you from optimizing any parameterized function you want, as long as its derivatives aren't too pathological. So no neural networks. What I have here is the partition function of the theory. This is written out where the parameters here have physical meaning. They correspond to the conformal weights of this theory, the combination of the operator dimensions and their spin. This partition function is a function of things that we call Virasoro characters. The Virasoro characters are functions of things called squared gnomes, which are themselves complex numbers. Right, so these are this like completely well-defined mathematical structure. All we're doing is adjusting the conformal weights of this theory to try to find ones that satisfy this condition of modular invariance. No neural networks. No matter what, I will have an answer that satisfies this known mathematical form. The question is, can I find locations of these orange dots, if you'd like, such that this equation is true? And again, it feels like machine learning should be perfect for this problem. So let's think like a machine, set this up as a machine learning problem. And we have those 4 ingredients that I mentioned: training data, loss function, a learnable function, and an optimizer. And in this case, training data is just, as I said, Monte Carlo integration. This formula of z of tau is equaling z of -1/tau, that has to be true for all values of tau. So you choose a particular measure and you do a phase-space integral over all values of tau. This is different integrals over different shapes of that donut shape. And you do that phase-space integral. You can see me doing a phase-space integral here, random sampling of tau, and then it's mirror -1/tau values. Again, tau is a complex number. So I just have Monte Carlo integration, great. Inside the integral is the condition that I want to satisfy, which I've squared, such that if this thing equals 0, then I'm good. So if my total loss is 0, then I have a CFT. My learnable function is just that partition function that depends on these dimensions. With a cutoff on the dimensions, basically a regulator, so that I can fit this on a computer. And then I'm going to apply standard gradient descent, just update these dimensions until I get something that minimizes the loss. Sounds straightforward. I started off my sabbatical with this problem. I said, oh yeah, this is just going to be a week or two, no problem. In fact, I'll be able to get a coding agent to write it for me. And turns out neither of those things are true. I actually hand wrote all the code for this paper, which was a fun thing of being a grad student again at some level. So the two aspects of this thing that definitely do work is Monte Carlo integration works well, and optimizing a partition function, that works well. But the loss function and the optimizer out of the box do not work. This approach on this slide fails dramatically at finding anything close to physical, which is a bit of a surprise. You might say, well, come on. I mean, shouldn't I be able to minimize this loss? Shouldn't that give me something that satisfies the condition that z is equal to z of tau is equal to z of minus 1 over tau? And gradient descent and its generalizations have been super successful in machine learning applications. Why doesn't it work here? So this is us thinking like a machine. Now we need to think like a physicist. And remarkably, the type of physicist that you need to think about to make progress on this loss function is not a theoretical physicist. You want to think like an experimental physicist. And what an experimental physicist will tell you is that a loss is defined not by its value, but by its uncertainty. That a success is not the residual. Success is your estimate of the uncertainty on that residual. And so what you need to do is you need to have uncertainties on your loss function, and you need to replace the mean squared error numerator with a chi-squared type of loss that has the uncertainty in the denominator. That is, you need to know not just whether you've satisfied the condition, but how well you've satisfied it. So if you don't normalize things in this way and you scan over different tau values, the loss scales over 20 orders of magnitude. Basically, you have an extremely ill-posed loss function, and if you try to optimize it, you'll get complete garbage. But if you do this normalization, if you normalize by the uncertainty, then you get this beautiful form where on a log scale, the loss values are peaked near log of 0 or of 1. So this is really like chi-squared per degree of freedom is 1. Like that's what you would learn about when you're doing experimental physics analysis of what it means to have a good fit. So here what we're doing is more like a goodness of fit test, and it satisfies quite beautifully, even though this is purely theoretical data, the type of behavior that you would expect if you were doing an experimental physics analysis using some Gaussian random noise. So by doing this normalization, you've turned this problem into kind of an ill-conditioned one into a well-conditioned one. But where does uncertainty come from? I mean, I told you I have this uncertainty. Don't I have to do a theoretical calculation to figure out that uncertainty? And the answer is, well, you go to the machine. So I need a robust method to quantify uncertainties. And so I went to Claude and asked a question. And unfortunately, I've lost the transcript of that session, so I can only reproduce it here. So we previously discussed the strategy for taking a known conformal field theory with central charge of 1 and deforming its partition function to mimic the Carney scaling behavior of a CFT with C greater than 1 in order to estimate uncertainties associated with truncating the primary spectrum. Can you remind me of that formula and where it first appeared in the literature? So essentially what we're doing here is we're saying we're trying to study theories that have central charge a little bit greater than 1. We have a lot of known CFTs at C exactly equal to 1. Those are my free boson theories. I want to do a deformation so that they scale in the way that a CFT should. And the way to do that is to use this formula, which I'm not going to explain here. All I'm going to explain is where this formula comes from. A similar construction appears in Benjamin, Collier, Fitzpatrick, Malone, and Perlmutter. Oh wait, Benjamin and Fitzpatrick are my collaborators. So I asked them, how do I estimate uncertainties? They had no idea. Claude identified their paper, which reinterpreted in a new light, gave me a way of estimating uncertainties. So this is this power of indirect AI/ML to help identify connections that would otherwise be difficult to see in the literature. Okay, so now we have uncertainties. That's great. Our loss function is well behaved. We still need a good optimizer. And now the way to make progress here is to think like a mathematical physicist and think about the geometry of your loss landscape. So if you do naive gradient descent tells a coordinate to shift according to a derivative. But anyone who takes a course in general relativity will know that you have an upper and a lower index, and you need to contract them with a metric. And so you need to compute a metric in order to actually have a well-defined optimizer. Of course, this is also known to people who do machine learning. These are known as second order or quasi-second order optimizers. So using that instead of stochastic gradient descent. Here we developed a new second order optimizer with Sam, Thomas, and Andre with the code name of Sven for singular value descent. You can download it from GitHub. I can tell you about in Q&A how it works. But you go from an optimizer that does a really bad job finding anything that looks anything like physical to something that actually starts to give you answers that look like a CFT. And if you want to know, this thing is basically some fancy version of a Gauss-Newton method if people want to know how this thing works. Okay, so now we have all of our 4 ingredients. We have our training data. We have our loss function. We have our function to optimize, the partition function, and we have the optimizer itself. And now we can descend into the modular bootstrap. We can start off from some random position where the loss, the chi-squared per degree of freedom, the uncertainty normalized loss is gigantic, 10 to the 13, 10 to the 14. And then with the STEN algorithm, as long as you take enough singular values, you can rock it down to chi-squared per degree of freedom of 1 and declare victory. And this loss landscape is wild. So here is an attempt to try to visualize this loss landscape. This is a loss landscape that has really tight, narrow canyon walls, such that if I try to move one parameter at a time, it only wants to move by like parts per million before the loss starts to get really big. But if I move a lot of parameters at a time, then you can actually find these kind of valleys that you can traverse. And in fact, there's evidence that we have that there's a complete continuous space of solutions here. Even though the canyon walls are really narrow, they fill out this like kind of fascinating network of rivulets going through this loss landscape. And this is related, if you want to ask me about it, to how overparameterization and generalization matter for solving this problem. Okay, so deep breath. We now have a chance to answer our scientific question from before, updating the space of candidate 2D CFTs. CFT experts plus optimization experts plus agentic AI plus me hand coding this all in Mathematica gives rise to the following candidates for possible CFTs. Remember, modular invariance is necessary but not sufficient. These candidates are ones that they might turn out to not satisfy some other property that I haven't tested, but this is a necessary condition. So if I can't find a solution, that's suggestive. And indeed, as I mentioned at the beginning, there's evidence for an obstruction to finding theories. These blue dots correspond to good theories. This blank region corresponds to a place where my optimizer could not find a solution. At small central charge and large spectral gaps, this seems to be excluded. Highly suggestive of an obstruction. Now, you might say, how do I know? How do I know that I just didn't run the optimizer long enough? How do I know, that there's not some problem in my setup? So I have to try to convince you that in the last part of the talk. Highly suggestive of an obstruction. But what I want you to take away is that I don't know how I would have even gotten this result without AI ML methods. I don't know how I would have even tackled this at all using traditional techniques. Remember, the traditional techniques gave me just this yellow sliver of excluded regions, which looks very different than this deep gap of excluded possibilities or seemingly excluded possibilities or an obstruction. So I needed to reframe the modular bootstrap in an optimization language. That's one thing I needed to do. But also I needed the help of Claude to reason through this conceptual issue of estimating uncertainties, which again, the experts couldn't tell me. And 48 hours of me talking to an AI helped find a solution to that problem. On the other hand, I also don't know how we would have gotten this result without physics input. To identify a tractable problem of relevance to experts in the field, that is, I really needed people who were CFT experts to tell me what was useful versus not. Developing a new optimization algorithm based on physics intuition for mathematical physics, this idea of needing a metric. And then pursuing statistical robustness even in a purely theoretical setting. And this is why someone like me who does particle phenomenology can make progress in this problem, because I have all these experimentalists talking into my ear, reminding me about the importance of uncertainties. And that turns out to be really important for this problem. So this is an example of advancing theoretical physics through a methodological merging of physical reasoning and computational algorithms. I think that this type of research you'll see more and more of this over the years. And now in the last 10 minutes, I want to try to convince you that we've actually learned something. And as we capitalize on these technologies, we still need robustness and reproducibility. We're not done with the story. How can I convince you that what I've shown you, this gap, this obstruction, is really real? So more generally, beyond the example that I showed you here, there's many opportunities in theoretical research via numerical optimization. So if your problem can be stated as find parameters theta such that f of x and theta equals 0 for all x, then it can be attacked with machine learning style optimization. This is known, very well known. Examples like this are like partial differential equations can be done in that format. And you've heard perhaps about physics-informed neural networks as a way of solving that. Bootstrap problems can be written like this way. So if your problem can be framed in this way, machine learning is a great technique, potentially. The lesson from our study, you have to know how close to zero you need to be to declare success. And this is about uncertainty quantification. And I don't know any shortcut other than detailed robustness studies to know whether you can declare success or not. So the rest of this talk is about these robustness studies, both using techniques outside of machine learning, but then also using techniques within machine learning. So what have we actually learned? With very high confidence, we found approximate solutions to the truncated modular bootstrap equations, almost by construction. That's what we tried to solve. This is showing the distribution of loss values. Blue correspond to those blue dots before, highly peaked nodes of log of 0. That's this chi-square per degree of freedom of 1. And then a bunch of theories that are really, really bad, very poor optimization that we don't think correspond to real theories. However, we cannot claim to have identified new CFTs. In fact, these examples are almost certainly not CFTs. And the reason for the experts is that the modular bootstrap does not constrain what are called operator product expansion coefficients. We'd have to do a more fancier bootstrap if we wanted to do those. So I can't claim that what I found are new CFTs. And also, we can't even claim to have excluded possible CFTs because in this primal approach of trying to find solutions, the absence of evidence is not evidence of absence. So maybe Sven just isn't powerful enough of an optimizer for this problem. So we're in this kind of awkward situation where all we can do is perform numerous studies to increase our confidence that this apparent obstruction is robust and reproducible. And except for at the very end, I don't claim that these are proofs of anything, but there are numerous opportunities for these checks to fail. And so I'll show these checks just to get a sense of kind of what we did to convince ourselves. So the first thing that you can do is just kind of look at the answers. So blue are good candidates, red are bad. And I've stared at enough of these plots that I can tell you that these blue spectra, in terms of the dimension and spin of operators, these ones look good. In fact, this pink one looks good too. In fact, it just barely misses the threshold. I set a 4 sigma threshold for it, and loss of 16 corresponds to 4 sigma. And so this just like barely misses it, and it makes sense. It's almost there. Maybe with a little bit extra optimization, it would have gotten there. And then these ones look really stupid. So, okay, visual inspection, things look the way that they should. We can check the definition of uncertainties. Let me skip this slide because of time. You can ask me during this for Q&A. I talked about Claude's approach for doing uncertainties. My human collaborators got really offended that Claude found a solution. The humans had a rebuttal to a different way of doing uncertainty quantification. And it turns out that the humans win on numerical accuracy, but AI wins on computational efficiency, and none of it makes any difference to the story. They all agree. So it's not the uncertainties being funny. Now we can start to get into some of the physics. Okay, so what has previously not been studied in the literature has been this constraint that when I have an operator, it has to have an integer value of degeneracy. That is, if I have a quantum state, I have to have 1, 2, 3, 4, 5 of those states. I can't have a fractional number of states. Now, this dashed black line here, that's what's known as the Hellerman bound, or the Hellerman-Collier-Lin-Yin bound. That's a bound that you get if you relax the condition of having integer degeneracies. So if you relax that condition, allow for fractional degeneracies, your optimizer should be able to saturate that bound. Okay, so we found this gap. We found red is bad, blue is good. We found this red region. That red region better disappear if I remove the constraint of integer degeneracy. And it does. You go all the way up to the bound. So with this additional freedom, Sven does find solutions that fill the allowed space when you float the degeneracy. So integrality appears essential for the obstruction. And this is also part of the reason why people don't see it. In standard dual bootstrap approaches, you don't actually, you allow for non-integer values. That's why people hadn't seen this previously in the literature. So that's a good sign. Okay, 2 more tests. If you lower the truncation scale, the uncertainty should be larger, so it should be easier to find solutions to the bootstrap equations. So numerically, I only kept operators whose dimension went up to 4. If I drop it to only keep operators whose dimension goes up to 3, then I have a less accurate solution. My uncertainty should be larger. I can hide more bodies within those uncertainties. I should be able to find solutions more easily. This red region should shrink. And it does. loosening the constraints does yield more apparent solutions. And for the experts, high dimension but low twist operators appear to be essential for this obstruction. And then I can go the other direction. I can raise the truncation scale. That should make the uncertainty smaller, so it should be harder to find solutions. So this red region should grow. Here, I'm doing this all by myself on Mathematica on my laptop. So I couldn't do a full scan, but with this reduced scan, you indeed see that the red region does grow. So tightening the constraints does reduce the space of apparent solutions, further evidence that things behave in the way that you expect. And then let me skip this closure test. Trust me that this works. Your answer should agree. It does. I'm really happy. Okay, so our paper comes out, and a postdoc at MIT, Kevin Langhoff, said, well, Jesse, you wrote this paper by hand. You wrote the Mathematica code by hand. I'd like to learn more about what you're doing. So maybe I can just try to reproduce it. I can take your GitHub repository, take your paper on the archive, and a human AI team, so Kevin using his version of Claude, could try to reproduce the results of our paper. And don't do it in Mathematica, do it in PyTorch. Okay, so he said, great, I'll reproduce it and see what happens. And this is ultra preliminary results. Okay, this is from Kevin 2 weeks after our paper came out, reproducing things. He actually has more recent ones that I'm not showing here. And what happens? This is what happened. So first of all, remember, I had this very coarse scan because I'm doing this on Mathematica on my laptop. I'm a horrible coder. I don't know how to do memory management. With help from a coding agent and a real optimization tool, Kevin found this result. And this is the delta max equals 3. So this is a relatively low truncation scale. Uncertainties are large. The allowed region blue is very big. And look at that resolution that he's able to do. These green circles correspond to the known theories. Look at what he's able to do with an hour on his laptop with an actual proper coding implementation. And then this is the 4. This is the one that was the baseline for our paper. And you see that same shape appearing. Again, completely independent verification. Of course, both things could have bugs in it, but okay. And then the thing that caused my laptop to get really hot and kind of stress my power supply, he's able to do no problem. 2 hours on the laptop, able to reproduce the results of what took me 2 weeks of optimization. And your reaction to this moment, right, is depends on like, what do you feel about AI? Like, are you worried about AI taking our jobs? I mean, AI is clearly going to take my coding job because I clearly did a really bad job with my hand coding. This is incredible. And we have 2 more panels here, right? So this is now taking this code and throwing it on a cluster, AI-assisted scientific discovery. And what's your reaction? Is your reaction, oh, let's stop all this and only do things by hand? Or do we want to take advantage of these tools? And this is the challenge that we in theoretical physics are facing about how do we convince ourselves about results when it is doing literally superhuman, or at least super Jesse analyses that I could not have done this by myself. Okay, so this ultra preliminary results suggestive of what? And by the way, for people who know about the conformal bootstrap, people will know that kinks often correspond to real theories. So it's kind of interesting that some of these kinks seem to be persisting. Maybe. They really do seem to be persisting. As you raise the truncation scale and you're getting more and more accurate information, you're seeing the emergence of fascinating structures. And in Kevin's latest results, which actually show that these regions here, which look kind of yellow, he fixed the optimizer, that they're now deep, deep blue. You find this very clear transition between a blue region and a red region with these like fascinating structures. I don't know if you can tell. It's like little like things like peeking up through. There's an obstruction to further obstructions. And we might actually be sitting on real theories starting to emerge at the boundary between the disallowed region and the allowed region. Okay, so that's exciting. So I gave a version of this talk, I guess it was, what, 3 weeks ago, 4 weeks ago? And before my talk, I said, maybe I should go back to my collaborator, Wei's, his PhD thesis. So he used a fully rigorous numerical strategy, the so-called dual bootstrap strategy, to define that yellow region that I mentioned before. And this yellow region, the details of how you get it don't really matter. This formula will make sense to anyone who's ever heard of semi-definite programming. But this yellow region is fully rigorous. So it's a numerical strategy, but once you find a numerical result, you're guaranteed that it works. And that gives you this yellow region. And I said, well, geez, let me just go back to his PhD thesis. Again, these are fully rigorous. No worries about the optimizer. If you find this yellow region can grow, then you can take that to the bank. It's guaranteed. I'll just take his PhD thesis and just let kind of agentic AI play with it. Okay. Again, the conclusion from the thesis was that these constraints are pretty mild. Well, what I can do is hand the JF article that Liam and Wei wrote, the Mathematica notebook that he used to generate the results, and then hand it to my unflappable research assistant. And again, there's like this question of how do you feel at this moment? Are you excited to see the results? Are you worried that an AI is going to kind of take over aspects of the scientific discovery process? No, in my case, I care about discovery and I care about a collaboration between AI and human. And it turns out that if you expand the search space from what was in Wei's thesis more broadly, then qualitatively you find the same thing that we were finding in the machine learning approach. These are now rigorous bounds. That little peak place here where you can't see where the bound decreases, that's also where this kind of funny notch was appearing in the other results. Ultra preliminary still, spot checked by a human, that's a good thing. But now we have rigorous evidence for an obstruction based on this technique. And in fact, we're using now both ends. We're able to do machine learning style techniques that are able to act much faster, and then rigorous mathematical approaches, but driven using agentic AI tools on the other end. And we hope that we can close this gap and actually learn something about these theories that up until now we knew very little about. So I see exciting opportunities for discovery from a combination of physics intelligence and artificial intelligence. I think that this is a really exciting pathway for our field. But of course, it comes with challenges, and hopefully, I've given you a sense of how, at least in my research efforts, we've been trying to address that. So with that, let me just recap. So I started off by telling you how many aspects of machine learning can be translated into the language of physics, and because of that translation into physics, I can, as a physicist, gain intuition about how these machine learning strategies work. We revisited this question that has appeared in theoretical physics for many decades, but revisited it through the language of optimization and found an apparent obstruction, a surprise, something that was surprising to my colleagues. And then we were able to use various strategies to convince ourselves of the robustness or reproducibility of the approach through a combination of standard analyses, but also AI enhanced ones. And so with that, let me conclude, and I look forward to any questions you might have. Thanks so much.